Okay. Yeah, good afternoon, everyone. Let's start. So first, homework 6 has been released today, and this will be our last homework assignment. There will be no more homework assignments, and we put the due to be a little longer than the usual. I mean, it's like it will be the 2 weeks plus 3 more days. It will be at the end of the week of the lecture week. So we're doing so to help to which that could bring more time for you guys to finish that, and hopefully that can relieve your stress at the end of the semester. And we will have again in addition to the final exam, we'll have a quiz this week and the quiz next week, and then the quiz are done, and then there will be one final exam in person, unfortunately, and then we're done. And hopefully, I mean, there's just about 2 weeks left. Hopefully everyone feels comfortable and smoothly transiting to the lovely summer. Okay, so in the last lecture, we talked about estimator. So it was based on a concept called statistics. So what is statistics? Assume you are doing some kind of experiments repeatedly. The most common used example is just flip the coin, right? So you flip the coin, you see the outcome, you can view it as a random variable. But in practice, you often have a chance to do the experiment many times, right? If all those experiments are done like independently, so after repeating the experiment for say 100 times, you probably will have like 100 random variables. Those random variables are called a sample, and these random variables are assumed to be RID. What does RID mean? What's the meaning of RID? Yeah, that's very fundamental term. I hope everyone is familiar with that. RID just means independent, identically distributed. Right? So basically, you're assuming you're going to collect a sample. Right? That sample consists of many random variables. Those random variables, they follow exactly the same distribution, but they're independent to each other. Right? Like you flip the coin for 100 times, you see 100 outcomes, right? Every outcome could be either heads or tails, right? And you got 100 such kind of ID random variables from which you want to estimate something, right? So the statistics are a given function. So if you have a sample X, which consists of, say, n ID random variables, so we can introduce a statistics which kind of aggregate the information within this n ID random variables. So this aggregation is fulfilled by some kind of function, right? So statistics is defined as the function of the ID random variables in your sample. Right? This function, there could be a variety of choices of functions, right? But anyway, overall, they kind of like aggregate information reflected through this collection of ID random variables. And we have mentioned several examples like sample mean, sample variance, or median, right? They're all different statistics. Okay, so the estimator, the so-called estimator, is a special type of statistics. So basically, if we know that your sample, those ID random variables, follow some particular distribution, for example, a Gaussian. But what we do not know is the parameters that control that distribution. For example, if you assume those ID random variables follow a Gaussian distribution, right? And for a Gaussian distribution, we need to know what is the mean parameter, mu, and what is the variance parameter, sigma square, right? And you just know, okay, the form of the distribution, but you don't know what exactly are the values of mu and sigma square. And what should we do? We want to construct an estimator, right? Suppose you do some random experiments, you collect a sample, right? A sample of size n, which consists of like n variables, n random variables, which following the same distribution. You want to infer the parameters of this distribution, mu sigma square, from x1 through xn. And this is called estimation, or more formally, statistical inference, right? And you can view like these samples, this sample x1 through xn as data. Why? Because you can do experiments, right? And take the observation of those of the sample, right? And given this data, you want to infer what are the parameters of the underlying distribution from which x1 through xn are generated. And that is how the estimator, this concept is motivating, right? An estimator is actually a function of those sample x1 through xn. And we mentioned that we usually use hat to indicate estimation. If we want to estimate mu, right, our estimation, which is a function of the ID random variables, we take the measurement from the experiments, right? We obtain an estimation of mu, we denote it as mu hat. Okay. Any questions so far? Okay. So, and here comes a very important concept, because the estimator itself is just a function of the sample, right? The sample is just a collection of ID random variables. That means the estimator is a random variable as well. It's just a function of multiple random variables. So that means when you do one round of experiments, you probably get the value of estimator C 0.5, right? When you do another round of experiments, that means you collect the values for x1 to xn, and then you calculate your estimator, you probably get another value like 0.52, right? So in essence, the estimator itself is also a random variable. It is not deterministic. Then comes a question, right? So it is random variable. That means like it is highly unlikely that your experiment, which give you the estimator's value, is exactly the same as the ground truth. For example, what is the mean parameter and the variance parameter for your Gaussian distribution? And your estimator is constructed by a set of random variables in your sample. It is random. So it is unlikely that doing one round experiment, you get some value, say 0.5, it will be exactly the same as the ground truth of mu. Then how do we know if your estimator is good or not? One perspective is looking into whether your estimator is biased. What does it mean? It means that if I take the expectation of my estimator, theta hat. If the expectation is exactly theta, then we say the estimator is unbiased. And if the expectation of an estimator is not theta, then theta is called a biased estimator. And the bias is directly computed as the difference between the expectation of estimator and the ground truth. Question? Everyone feels comfortable? Great. So unbiased estimator, though, still cannot guarantee that you get the ground truth after one round of experiments or measurement. But it can give you a asymptotic guarantee in that if you keep running your estimation procedure, right? And your estimator on average will get closer and closer to the ground truth. How can we see that? Yeah. To facilitate our understanding here, I want to talk about things a little bit deeper, right? So suppose you do many estimation, right? So remember, the value of estimator is to compute some function over the sample, right? And every time you got a different set of values for the sample. So imagine that you're gonna do this for n times. So you got n estimators, right? Theta 1 hat to theta n hat. Right? So and I want to average out these n estimators. Right? If my estimator is unbiased, my average will also be unbiased, right? Why? If each of my estimator is unbiased, meaning that their expectation is exactly the same as the ground truth parameter theta, right? And when I average them, my expectation is what? What is my expectation? Yeah, it's still the parameter theta. Why? Because if you take expectation over this guy, right? Remember the linearity of expectation, right? You just apply the expectation over every theta hat g, which is also the parameter, right? You just average a set of same values, right? It'll be theta. Does it make sense? Right? So all those guys are ID, right? And they are unbiased, meaning that you take expectation of everyone. It's just the ground truth. Right? That's the definition of unbiased estimator. Now you take the average of these guys, right? What's that? Right? Applying the linearity of expectation. Right? Linearity means that you take the linear combination of the random variables. The expectation of linear combination of random variables is the same as you take linear combination of the expectation. Right? So this is the same as you first do the expectation over every estimator and then do the average, right? So each estimator is unbiased. So that means their expectation is theta, right? You just add up the same theta for n times and do the average. Of course, it will give you theta, right? Does it make sense? And now we should recall the central limit theory we discussed before, right? What is central limit theory? It basically means like if you have a set of ID random variables, their average will approximately converge to Gaussian distribution, right? That's the central limit theory. You don't need to memorize the form, right? So, but basically it means that your average estimator subtracted by its mean and divided, which is the theta, right? And divided by the variance of each estimator, which we denote by sigma square n and by n, right? Will approximately become a Gaussian, right? That's the central limit theory. In other words, that basically means your average estimator will approximately be viewed as a Gaussian distribution with mean theta and the variance being sigma square over n. N is the number of the rounds of experiments you get, right? So you see that when n goes to infinity, theta hat average will converge to theta, right? And you see the variance is decay fast, right? It's decay along with n. Question? Everyone feels comfortable? Yeah, this just to show that, okay, if you have an unbiased estimator, what's the benefit? This kind of analysis, don't worry, you won't be, it won't appear in the final exam. But we want to give you a sense that if you have an unbiased estimator, as you do more and more estimations on average, your estimator will quickly approach the ground truth, right? However, if your estimator is biased, like even you do this average, you can have your variance, right, to get smaller, right? But your mean is not necessary to be the ground truth. So there is always some gap between the ground truth and your estimation, no matter how many rounds of experiments you're doing. Does it make sense? Question? Right? If you're unbiased estimator, your mean is not necessarily theta, the ground truth. It could be theta plus some gap, right? Like even you do like a million rounds of experiments, making this variance to be very tiny, right? It's very small, but your average of those estimators will still have some gap between, significant gap between you and the ground truth. Okay, I mean, if you feel uncomfortable about this analysis, that's totally fine. But just have some kind of sense why at first, whenever we develop some kind of estimator, at first our goal is to seek for some kind of unbiasedness, because some kind of asymptotic convergence guarantees. Okay. So here we give one most commonly used example of the unbiased estimator. So the sample mean. Okay? So x and hat here is just the average of the n ID random variables, right? If we estimate the mean of those random variables with the sample mean. Then the sample mean is unbiased. Why? Why is the sample mean is the unbiased estimator of the mean, of the true mean? Yes, exactly right. That's just fits the definition, right? The sample mean, as we mentioned, is a random variable, right? If you take expectation of the sample mean, it will give you exactly the true mean, right? So that means the sample mean is unbiased because its expectation is exactly the true mean. Okay. So now let us look at another estimator we call sample variance. So what is sample variance? Suppose your sample are x1 throughout xn, right? So the sample variance takes a little bizarre form, which is 1 over n minus 1, the summation 1 to n xj subtracted by xn square. So you see that it is the sum, it is the square, it's the sum of the square of the difference between each sample, each random variable xj and the sample mean, and then divided by n minus 1, not n. Right? And the sample mean, let us write down the definition again, is just the simple average of all the random variables in your sample. So why do we use 1 over n? It seems like we should use 1 over n rather than 1 over n minus 1, right? But here, using the factor 1 over n minus 1 has a significant meaning. It will guarantee that your estimator is unbiased. What does it mean? It means the expectation of your sample variance will be the true variance. Again, sample variance is a function of the random variables x1, x2 to xn, right? So the sample variance is the random variable, and we take expectation of the sample variance. It will give you exactly the true variance of each individual random variable. Everyone understands the statement here, right? We conclude that the sample variance is an unbiased estimator of the true variance. Any question regarding the statement here before we proceed to show this? Okay, great. So next we would like to we would like to show why this is the truth, right? So we would like to leverage the definition. Right? We're going to calculate the expectation of the sample variance directly. So according to the definition, you're going to take expectation of this whole thing, right? You're going to take expectation, sorry. of this summation, right? And according to the linearity of the expectation, you can just move expectation inside the summand, right? So it will be 1 over n minus 1, j from 1 to n, expectation of xj subtracted by the sample mean, take the square, right? Does anyone disagree? Okay, so then the remaining thing is that how do we compute the expectation of every square term, right? So we just do some expansion, right? So this is square term, so that means we're gonna take expectation or xj squared plus x hat n squared subtracted by 2 xj x hat n, right? You just take you just expand the square term, then you just calculate the expectation of each individual term, right? Combine them, right? That's again the linearity of expectation, right? Question? Okay, then let's just do this, right? So first one, xj squared. What is the expectation of xj squared? We know that each xj, right? We have a expectation of xj to be mu. We have variance of xj to be sigma square, right? So what's the expectation of xj squared? Any thought? Any guess? To answer this question, we need to go back to the definition of variance, right? So the variance is defined as, we actually, remember we have two possible definitions, right? So let us use one definition, which is the variance of xj equals to the expectation of the square subtracted by the square of the expectation, right? And remember, I have two definitions. One definition is that, okay, you're gonna take the expectation of the square of the difference between x and its expectation, right? But you can also use another one. You subtract the expectation of square by the square of expectation. So we know this guy is sigma square, and this guy is mu, right? Then it gives us directly expectation of square is sigma square plus mu square. Does it make sense? Question? Okay. So we get our first result, right? Expectation of xi square is sigma square plus mu square. So how about second one? The second one is the expectation, the sample mean square, right? So how do we compute that? Yes, exactly, right? So we follow the same method to compute, right? So variance is equal to expectation of square is equal to variance plus square of expectation, right? The K is how do we compute the variance of the sample mean, right? This is some result we discussed before, right? So because sample mean is just the average of n RID random variables, so the variance of sample mean is the variance of each individual random variable divided by n, right? So then you can immediately get the expectation of the square of the sample mean is variance sigma square O(n) plus mean square, right? Plus mu square. Question? Okay. So the last one is the expectation of xj and xn square, xn hat, the sample mean. Right? This one is a little bit non-trivial, right? We want to compute the expectation of xj, hxj multiplied with the sample mean. How do you compute this? Any thought or any guess? Yeah. So we look into the full form of the sample mean, right? You just substitute, and then then let's check what is going on. So you know the sample mean is just the average of the RID random variables, right? So you just multiply xj into each summon, right? So you're gonna have a summation from 1 to n. You're gonna multiply xj with xi, then take expectation. Does it make sense? So we just multiply xj inside the summation and then apply the linearity of the expectation. That means you just apply expectation over each product and add them together and do the average. Okay. So here, there's one interesting observation. What if I is not j? So I and j are not equal to each other. Then what is exj times xi? What's that? Say I is 1 and j equals 2, right? So what is the expectation of x1 multiplied with x2? And then what's the result? Yeah, almost there. Yeah, I'm just talking about this term, right? What is the expectation of xj times xi, right? J and I are not equal. In this case, remember, xi and xj are independent to each other, right? They have nothing to do with each other. So that means their expectation can be written, the expectation of their product can be written as the product of their expectations. So you can write it as xj is expectation times xi is expectation, and both expectations are mu. Right? So this gives you mu squared. Does it make sense? Any question? Okay. And there's another case where I is the same as j, or j equals to I. In this case, we cannot decompose, right? Because xj is not independent of xj, right? Then it becomes xj times xj, which will be expectation of xj squared, right? And what is the expectation of xj squared? No, I'm talking about xj squared. It's not sample mean square, right? So the result we have just calculated, right? It's just mu square plus sigma square, right? Question? Okay, so then when we all add them together, you see that for every product, the expectation will always contains mu square, right? There's only one case where I is the same as j. Your expectation has an addition term, sigma square. So that means when you add them all together and then divide it by n, you end up with mu square plus, because you only have one term which has the sigma square, right? And then you divide it by n. So you have this mu square over n. Question? That's what is listed here, right? What listed here. Okay, so now we have being able to compute the expectation of all the three terms, right? Here, here, here. You just substitute them into there, right? So this is just a quick check, right? So it's sigma square. So remember, expectation of xj square is mu square plus sigma square plus mu square. And the expectation of the sample mean square is sigma square over n plus mu square. And this guy is mu square plus sigma over n, but you need to multiply with 2, right? So you're going to subtract it by 2 mu square minus 2 times sigma square over n. Okay. So then you can see the mu square will cancel, right? And then you have the sigma square subtracted by sigma square over n. If you merge them together, it will give you n minus 1 times sigma square. Right? I mean, if you don't follow, that's fine. I mean, we just recommend you guys to replicate all those derivations after the class, right? So now each term, you have this guy, right? You just add all those terms again, all the way together. You add them n times. So after the summation, you get n minus 1 sigma square, right? Now you divide by n minus 1 because it's the outer factor. So eventually you're got the expectation to be sigma square, right? Any question regarding the idea here? And from this, we can see why when we choose sample variance, we're gonna divide the summation of the squares by n-1 rather than by n. This is just to cancel out the factor here and to ensure we get a unbiased estimator. Question? Okay, let's rest for a few minutes and then continue. Mm-hmm. Yeah.
First, the question B is asking us if the result of one is independent from the result of array.
Mm-hmm.
And I used what I got from the previous problem, which
Mhm.
proves that USA losing is independent of array,
Mhm.
to answer this question. Is that like an okay to go about?
Yeah. But you need to make sure that all choices of H and A will maintain this equation.
Yeah.
Yeah.
So does that mean I have to check all choices of home and away?
Yeah.
Okay.
Yeah.
Cool.
That's
Thank you.
our definition.
Right.
Yeah. Hey.
Question for just the first one, I think I don't understand what this is saying because do not win at least one game is like losing you could be losing both or you could be tying both, right?
What's the probability of sequence not win? Yeah, you could. That means like you could lose.
Like you could lose both. So I don't understand if you're supposed to find, for example, the probability of winning both and then take the complement, so you would get 0.7, or should you do the total probability of losses and ties, and which would be 0.25?
It talks about the game with the German team. What do you mean by both loses?
Like, I don't understand how to basically solve this. I don't know if this is correct.
Um,
I just don't understand if it's asking for total probability of like 2 losses and 2 ties, or 1 loss and 1 tie, or if it's asking for.
okay, so I can now tell you how to do this, but uh, from the problem, the meaning of the problem, it means the USA does not win at least one game, right?
Yeah.
And for example, um, lose is definitely ruled as one case, right?
Mhm.
And when away is 0, and then no matter like home takes 0, 1, 3, are all be viewed as USA loses, right? So you have to consider the total probability in this kind of like sense.
Oh, wait, but this table is all of USA. This is the table for the USA. So wouldn't you be considering? You'd be considering everything, right?
Yeah, you consider everything.
But I don't. I don't know if you answered my question. Like, it's like does not win at least one game means they lose one or they lose two. So you have to find like the probability as if they lost both.
Not levels, like you lose 1 or lose 2, right? And you got lose 1, lose 2. Lose 1 is a case, lose 2 is a case, right? You need to calculate total probability.
Mhm.
You either lose one, sorry, you either lose two, right? But you cannot, you cannot include win. Solution win, right?
You can't include win at all because they could win one. Those are just making me think you should include some sort of data from the wins.
Mhm.
Because you could win one, but you lose the other one.
The ULC does not win at least one game. Does not win at
Okay, then
least one game.
that
That
ca-
means you
okay.
don't lose anything, right? You
Okay.
can be lose or you can be tie, right? You cannot win anything.
So if it's like does not win at least one game, it just means that they can't win both. So you would just not include this data and find the total probability of this, and these. From my understanding. Which means this is wrong. Right? Because like
I think your understanding now is correct. I didn't check your answer here.
okay, because
Uh,
like tell me if I'm thinking about this right. Like if you can't win at least one game, that means you can't like this data win and win is like winning both. So that you can't include this 0.3. But like now, for example, this piece of data is win one, but tie the other one, or win one and lose the other one.
mhm.
Does not, oh, and then, okay, so I think it would just be the total probability of these,
Yeah.
all of these.
Yeah.
Okay. Okay. I think that's right. Okay, thank you.
Okay. Let us continue. So as we just showed, right? You choose sample variance, which means that you're gonna have this factor 1 over n minus 1 in front of the summation, and xj subtracted by x, the sample mean square, right? It will give you unbiased estimator. So the expectation is sigma squared, right? But in some scenarios, people use 1 over n instead of 1 over n minus 1. Right? So if we calculate this guy instead, the summation is the same, right? I just look at the summation of the square the difference between each sample and the sample mean, but then I divide the summation by n. And if I look at the expectation, you will see that it is n minus 1 over n times sigma square. So this is actually a biased estimator because it's not exactly the same as the ground truth. Does it make sense? And it's very easy to show this. Okay. Oops. It's very easy to show this because this guy can be can be written as 1 over n times n minus 1 and over n minus 1, right? So you just move this factor outside of expectation, and the inside expectation you put 1 over n minus 1 here, right? Remember, if you multiply these two fractions together, it will end up with 1 over n. But now if inside the expectation, if you replace 1 over n by 1 over n minus 1, it will give you sigma square, right? And then you multiply the factor outside, which is n minus 1 over n times sigma square. It's a simple trick. Question? I mean, if you feel like you didn't catch up with this, it's fine. After class, take a look at the slides. You get to know what I meant, right? So you basically rewrite 1 over n by the product of these two factors, okay? And then you move one factor outside, and outside of expectation, and inside you have 1 over n minus 1. And from the previous result, just get the expectation of 1 over n minus 1 of this summation is just sigma square, and then you get the result. Okay, let us look at another example. Suppose the random variable follows a Bernoulli distribution. By Bernoulli distribution, it means that you got some probability to see success of failure, right? One most commonly used example is the coin, right? You flip the coin, you have some probability p to see heads up, and 1 minus p to see tails up. So the PDF for a Bernoulli random variable takes this form, right? P to the power of x, 1 minus p to the power of 1 minus x. And the Bernoulli random variable can only take binary values, which is either 1 or 0. Any question? We first quickly review what is the Bernoulli distribution. It just basically describes the flipping the coin, right? You got chance p to see heads up, which is 1, and that means you got chance 1 minus p to see tails up, which is 0. So now we also want to conclude that the sample mean is an unbiased estimator for p. Right? The setting is that, okay, suppose I flip the coins for many, many times. So I got a collection of ID Bernoulli random variables, x1 through out xn, right? My sample mean is just the average of those outcomes. Then our claim is that xn hat sample mean is an unbiased estimator for p. Why is this correct? Yeah, we would like to verify through the definition, right? So we just need to check whether the expectation of our sample mean is p or not, right? So the expectation of sample mean is defined as here, right? We know that it is just the average of the expectation of each individual random variable, xj, right? So now for a Bernoulli random variable, what is its expectation? Right? Remember, each xj is either 0 or 1, right? So for a Bernoulli random variable, what is its expectation? Yeah, it's just the p. Why? I mean, we can just verify through the definition, right? So the expectation of xj is the probability you'll see xj is 1 times 1, right? Plus the probability you see xj is 0 times 0, right? And this guy is simply 0, right? This guy is p, right? So it's a well-known conclusion, a well-known result that for the Bernoulli random variable, the expectation is the probability, is the chance to see success. So that means the average of all those n expectations will just be p. Right? We see that the expectation of the estimator is exactly the same as the ground truth. So we conclude the sample mean is an unbiased estimator of P. Question? Everyone feels comfortable? Great. Okay. The last thing we want to talk about is the so-called estimator efficiency. So what does it mean, right? Suppose you got two estimators, and they are both unbiased, meaning that if we denote the ground truth parameters as theta, right, and you come out two estimators, and for both estimators, you have their expectation to be exactly the same as theta. Then to compare the two estimators, right? We know that they are both unbiased, so we don't have we have nothing to say what's the difference between their accuracy, right? So, but we could look at the efficiency. So what is efficiency? We look at the two variances, the two estimators whose variance is smaller. We say theta 1 hat is more efficient than theta 2 hat if the variance of theta 1 hat is smaller than the variance of theta 2 hat. So what does it mean, right? It means that suppose this is your ground truth, right? And you have two possible estimators. One is theta 1 hat, one is theta 2 hat, right? For theta 1 hat, you know, it is random. So different random experiments will have different values, right? But if you look at the variance of theta 1 hat, you may say, okay, this is the range of its variation reflected by the variance. But if you look at theta 2 hat, right, it will, although on average, its expectation is still the ground truth, but on average, it has a larger span than theta 1 hat. Then we see theta 1 hat is more efficient than theta 2 hat. Why? Because it just indicates on average, theta 1 hat is closer to the ground truth than theta 2 hat. That's why people call it more efficient. Question? Everyone feels comfortable? Okay, great. Okay, that's all about the estimator, the statistics and estimator, right? Okay. So now let us introduce a very, very important concept in statistics, practice, and inference. It is called confidence intervals. Right? You probably have seen this in numerous places, but now we're gonna give a more rigorous definition. What it is confidence intervals, and usually, how do we compute the confidence intervals? Okay. So we have introduced the estimators, right? We have discussed estimators. So if you have a collection of the RID random variables, right, and you can calculate some statistics over those random variables to give some point estimate. For example, what is the mean of the Gaussian distribution? What is the variance of the Gaussian distribution? What is the probability P in a Bernoulli distribution, right? So, however, all those estimates are just giving one number. For example, sample mean. If you have collected 100 ID random variables, their values, you take the average, it gives you some estimate. This just to give a single number, right, which we call the point the point estimate. The point estimate, although it's very useful, it gives you a single best guess of the parameter based on the data you collected from your random experiments or collected from your measurement. But it is not, often it's not sufficient for us to make decisions. The reason is we don't know the associated risk. Right? And also the point estimate also has some errors. Right? We want to control the risk. For example, what is the NASDAQ or whatever stock price tomorrow? You can come out some like a sophisticated methods. You got a point estimate of the stock price tomorrow, say 383, right? $1 per share, right? But only giving this single number won't be sufficient for us to make decision for investment, right? Because I don't know how confident your estimation is. If you can give me a interval, the range, right? Say, I have a very high confidence, say, I have 95% of confidence that tomorrow's stock price will be landed in a range like 381 to 385. That would be much better. Then people can have much more information to estimate the risk of the loss and then make a decision. That's what the concept called confidence intervals come from. So the confidence intervals are trying to estimate a range where the parameters like falls with a given probability. Right? You know some unknown parameter, it is a constant, it is unknown, and there must be some ground truth there, but you don't know what the exact value of that ground truth. And then I want to come out a confidence interval. And I can claim that the ground truth will fall in these confidence intervals with high probability. And then I can make a decision, right? Say I know with 95% chance tomorrow's stock price will fall in this range, and then I can decide whether I'm gonna invest all of my money or just a portion of them. Right? And that depends on how I'm robust to the risk. Okay. So let us be more formal, right? So here's the definition of the confidence interval. So let x1, x2 throughout xn be a sample from some distribution f, right? So it's ID random variables, right? They're sampled from the same distribution, and this same distribution have some parameter theta. So for example, the mean and sigma, the variance in the Gaussian distribution, or the probability P in the Bernoulli distribution, right? Or the lambda in the exponential distribution. And then we define 100 times 1 minus alpha confidence interval. That means there's 1 minus alpha percentage. Well, I wouldn't say that. It's just a percentage. 100 minus 1 minus alpha, 100 1 minus alpha percentage confidence interval. And this confidence interval is for the parameter theta, which is usually unknown. This confidence interval consists of pair of Ln and Un. So Ln is the lower bound, Un is the upper bound, such that the probability that the ground truth parameter theta falls in this interval is 1 minus alpha. So see, there might be some like a very complicated distribution, right? So the governing parameters of this distribution is theta, right? And then if I can find out an interval, sorry, you can find out an interval Ln and Un such that the probability of this interval, including theta, is 1 minus alpha. Then we say this interval is a 100 times 1 minus alpha percent confidence interval. That's the definition. Any question? Everyone feels comfortable? Okay, great. So when we try to find out such a confidence interval, we want this confidence to be as large as possible, right? But of course, it is really very hard to find a confidence interval to correspond to very, very high confidence, like 99.999 confidence. That will usually make this range to be very, very large, because it will, the larger Ln and Un, the more likely theta will fall in, right? And in the extreme case, will be minus infinity to positive infinity. Then theta n falls in this region, falls in this range with probability 1, right? But that's not, that is practically nonsense, right? So in practice, right, people often choose alpha equals to 0.05. That basically means I want to find out a confidence interval such that the probability this confidence interval includes theta is 0.95. The interval has 95% of chance to contain the ground truth theta. So this is the common choice of alpha. Question? Okay. So let us try to identify the confidence interval for a given distribution. Then we try to extend it to the case that you don't even know the form of the distribution. So suppose my random variables follow a Gaussian distribution. So x1, x2, and so on, they're all ID, and each random variable follows the same distribution, which is Gaussian with mean as mu and the variance as sigma squared. So if we do some linear transform of this random variable, so we first compute the sample mean, right? Suppose you got n ID random variables, which we have mentioned before, this basic setting, and we calculate the sample mean. Which is just the average of this n ID random variables, right? Then we can perform a linear transformation over the sample mean, which we define by Zn here. So Zn here is simply as xn subtracted by mu and divided by sigma over square root n. So we know that Zn will follow a standard Gaussian distribution with the 0 mean and 1 as the variance. Why is that the case? Why is that true? So first, Xn also follows a Gaussian distribution, right? Yeah, we talked about that before, right? So you got a set of Gaussian random variables. If you just linearly combine them, the combination will also be a Gaussian random variable. So the sample mean Xn is a Gaussian random variable, and the mean of Xn is simply mu, right? It's just derived, right? The expectation of the sample mean is just the expectation of each individual random variable. And what's the variance of the sample mean? Could anyone recall? It's sigma square over n, right? Yeah. So if we look at, oh, sorry, see another lecture slice, right? So it's here, right? The expectation of the square of the sample mean is mu square plus sigma square over n, right? And you subtracted it by the variance, which is this guy. Mean, which is this guy, you get sigma square over n. Right? So now we know the mean and the variance of the sample mean, and we know that the sample mean follows the Gaussian distribution. That is enough for us to know what's the Gaussian distribution Xn hat follows, right? So the mean is mu, and the variance is sigma square over n. Right? So the linear property of the Gaussian random variables tells us that if you subtract a Gaussian random variable by its mean and divide it by its standard deviation, right, which is sigma square over n, this new random variable is simply the standard Gaussian distribution with mean 0 and variance as 1. That is the Zn here. Right. So now if we want to find out a 1 minus alpha, 100 1 minus alpha % confidence interval, we just need to find out a interval such that the probability Zn falls in this range is 1 minus alpha. Right? So if we look at here, right? So Zn is the standard Gaussian distribution. So if we want to find out, so this is Zn, right? If we want to find out a region or interval such that the probability Zn falls in this region is 1 minus alpha, so we can choose a quantile, right? Remember, what is quantile? What is quantile? Quantile is just the position or the value such that the probability, the random variable below that value is the given probability. So that's why we can choose Z. You can choose quantile half alpha and minus half alpha, and then you use these two quantiles to form the range, and we can calculate that the Zn falls in this region with the chance 1 minus alpha. And Zn is a linear transformation of Xn, so you can immediately get the confidence interval for Xn hat. Okay, that's a little bit over time. So let's continue our discussion on Thursday, which we're gonna give more details. Okay, see you on Thursday.